So we've spent quite a bit of energy and time over the past 2.5 weeks or so talking about strategies for factoring polynomials. And the principal reason that we did was that it gave us the ability to solve new kinds of equations that we didn't know how to solve before. So just rewinding us to a quick example. Suppose I go back to here. So if we have a polynomial equation, the best strategy that we know at this point in the semester for how to solve a polynomial equation is, if we can do it, to factor that equation. Assuming that the other side is equal to 0, that lets us then split each of the two factors into its own much simpler equation, and then solve each of those equations independently. So right now, this is both the only strategy that we have for solving polynomial equations, and it's also really the only thing that we use factoring to do, other than to sort of do it to practice it for its own sake. So the next two topics, really, that round out our semester, kind of give us two more things in this same vein. One thing that we can use factoring to do that we haven't used factoring to do yet, and that's going to be to analyze expressions, algebraic expressions that look like fractions, but whose numerators and denominators are polynomials and not just numbers. And so for the same reason that factoring numbers was useful when we studied fractions, factoring polynomials will be useful when we study fractions that are made up of polynomials. We call those rational expressions. So that'll be the first thing that we do. And then the last topic for the semester takes us back to these kinds of problems, polynomial equations, in particular quadratics, degree 2, and gives us another method for solving degree 2 equations that doesn't involve factoring. So that kind of completes the picture. It gives us one more way to do something that we used factoring to do, and also one more thing to do with factoring that we haven't done yet. So I'm hoping today that we can get through as much of this picture of rational functions as possible. Really, these three sections in our text are the ones that I want us to focus on. First, we'll just get an introduction to, this says rational functions, but we're going to think of them as rational expressions because we're not equipped in this course to tackle functions in their entirety. But we'll think about what rational expressions look like, how do we simplify them, how do we understand them. That'll be phase 1. Phase 2 is going to be to take rational expressions and multiply and divide them one by another. This is exactly the same discussion that we had 11 weeks ago, maybe longer, when we talked about how to multiply and divide fractions. Very same principles, the very same arithmetic underlies what we'll do with rational expressions today. And so you're working all the same muscles that we had to work back then. Same strategies, just now with expressions, variables in the numerators and denominators, and not just numbers. And then, of course, because multiplication and division is the low-hanging fruit, addition and subtraction is the one that really requires the most time and thought and taxing attention. Because just like with fractions, when we add and subtract rational expressions, we have to worry about, what's the one thing we have to worry about when we add and subtract fractions that we don't have to worry about when we multiply them? What makes adding or subtracting fractions more challenging than multiplying or dividing them? Common denominators, right? So that's just as it was with fractions, same story here, right? The strategy is identical to when we did this with fractions that have numbers in the numerator and denominator. And what makes it more challenging to add and subtract is that we're going to need common denominators for our rational expressions first. So when we first started studying fractions, one of the first things we talked about was how to re-express a fraction into its lowest terms. Right? Back then, we would take a fraction like, I don't know, 12 over 32 or something like that, and ask, is this the simplest way that I can write this fraction? And for this fraction, the answer is no. But how do I know? How do I know that there is a simpler way to express the fraction 12 over 32? They're both even numbers. So both the numerator and denominator are even. That means what?
That these two can go into
yeah, exactly. That I can write each of them as something times 2, right? So if I think about it at the level of factors, 2 is a factor of the numerator, and it's also a factor of the denominator. And so if I factor each of those two numbers, factor uses a verb there, if I factor each of those two numbers, I find out that they have a factor that they share in common. And so what do I do then to make this fraction expressible in lower terms? What do I do with that common factor? I divide by it in the numerator and the denominator. That's one way of thinking about it. But the way in which most algebra students remember this step is not as a division, but instead as an annihilation. Because that's really what happens when we divide by 2 in the numerator and the denominator, is that that factor of 2, which lives both places, ends up just going away. So when I divide by that 2, what I end up with is a new fraction that has the same value, but which is expressed using smaller integers in the numerator and the denominator. And then conceivably, the process could continue. What about 6 over 16? What can we say about that? Yes, exactly. Because again, 6 and 16, both have this common factor of 2. 6 is 3 times 2. 16 is 8 times 2. And therefore, again, we can divide the numerator and denominator by 2. And what ends up happening if I divide the numerator and denominator by 2 is that those 2's cancel away. Gone, gone. And we therefore arrive at a still simpler fraction. Has the same value as the one we started with, but which is expressed using smaller integers. And now that we've arrived at 3 over 8, we know that we're done because why? 3 can't be divided anymore. For there's no way for us to factor the number 3 into anything meaningful other than 3 times 1. And neither 3 nor 1 goes evenly into 8. So neither one of those is, well, 1 does, I'm sorry, but 3 doesn't. And if I try to cancel a 1 out of the numerator and denominator, that's going to be an invisible cancellation. Right? We're just going to end up with 3/8 again. And so at that point, we're in our lowest terms, because the only common factor between 3 and 8 is the trivial factor of 1. And at that point, we have to stop. So that very same process of, first of all, identifying what are the factors of the numerator and denominator, and then secondly, canceling out, dividing by, those factors which are common in the numerator and denominator, will also work when the numerator and denominator of our fraction are expressions rather than numbers. So identify all the factors, and then cancel those that are common. And I'm breaking this out as 2 steps, because very often people will forget the first one. It's not going to be as easy to do in the first example we're looking at, but it's going to be real easy to do in the next one. So I want to think of these for now as being 2 separate steps. So with that ideology in mind and this example kind of guiding us, let's take a look at this ratio of 2 expressions. 4x to the 3rd times y is our numerator, and 2x is our denominator. So I'm going to ask the question first. What are the factors, what are the numbers and expressions that go evenly into the numerator, 4x to the 3rd times y? What are the factors that make up 4x to the 3rd times y? Let's start with a 4. What are the factors of 4? 1 and 4, or 2 and 2. And I'm choosing not to write the 1 and 4 because canceling a 1 isn't going to do anything for us. So I'm going to prefer to think of this as 2 and 2. Okay. How about x to the 3rd? What is x to the 3rd at the level of, what are its factors? Yeah, x to the 3rd. X written 3 times is another way to think about that, right? X times x times x. And then I have a y. So my variables here, my x's and my y, those are kind of playing the role of our prime factors. We can't break a single power of x out any further. But we could break x to the 2nd or x to the 3rd out into a repetition of multiplication by x. So there are all my factors upstairs. Meanwhile, downstairs, in my 2x, there's not a lot of meaningful factoring to be done, but it still might be a good exercise for us to identify the factors. 2, well, the only factor of 2 is 2 itself. And then x, well, the only factor of x is also x itself. So I'm just going to kind of write that. So now I've identified upstairs and downstairs what all of the factors are in my numerator and my denominator. So my step 1 is done. Now, I have to do this process. Right? So after we've identified what the factors are, those factors that are common to the numerator and denominator can be divided away to make our expression simpler. So what's one example of a factor that both my purple numerator and my green denominator have in common? 2. So what we can do then is divide by 2 in the numerator and the denominator. And when I do that, that factor of 2, which I've written here, is just going to be canceled. And then I would be left upstairs with 2 times x to the third times y, and downstairs I would have only an x left over. So that's going to make my fraction a little bit simpler. I'll write it like this, 2x to the third y over x. But there's another factor that these still have in common. What else? Yeah, a single power of x. So we can divide that away as well. You'll recognize this, by the way, as another face of the strategy that we did when we first learned the properties of exponents. We simplified expressions that looked very much like this one. And we decided that the guiding principle in how we did those simplifications is that dividing powers is the same thing as doing what to their exponents? If I divide these two powers of x, what do I do with their exponents, 3 and 1? Subtract them. And that's another manifestation of the fact that after I cancel those two factors, we end up with only 2 powers of x that survive. X to the 2. Then I have a y. And then downstairs, I ended up canceling both of the factors that I have down there. And so I end up with just a 1 in the denominator. Multiplicative 1, the invisible multiplication by 1. Which I can write if I want to, but probably in my final answer I'll simplify so that I don't have to. And I'll just write my final answer as 2x squared y. So there was our two-step process. Identify what are all the factors, and then for those factors that are common to the top and the bottom, we'll just cancel them away. And that's our strategy for simplifying a rational expression. Just the same process that we did when we simplified fractions once upon a time.